Welcome back. In the previous class, we discussed the content which are related to the first law of thermodynamics. Now we discuss the content which are related to second law of thermodynamics. That first one is the entropy. So entropy, the meaning of entropy is the randomness and disorder. Actually, it is the concept based on this concept. One of the concept based on this second law of thermodynamics is developed. This concept says why in the universe some reactions are spontaneous, why some reactions are not spontaneous. For example, when I drop the glass, it will immediately breaks. Okay, so it is a spontaneous reaction. But the glass pieces which were there, they coming together and becoming a glass. It is not a spontaneous, and it is a very less probability. So that is the entropy says in the universe why some processes are spontaneous. For example, from A to B. In other words, it says that the probability of A to B is very and the probability of from A to B occurring is very high. In other words, the randomness is very high. In other words, this entropy is very high. The process which are having the high entropy, then those processes are a spontaneous process. For example, in the same manner from the A to C, in that if the probability of happening from the A to C is less, then in other words, randomness is less. In other words, entropy is less. The process which are having the low entropy, then the occurring of it is likely not spontaneous. So this concept says that. So the quantitative description of entropy is equal to ds is equal to dq. Means the change in entropy is equal to change in heat energy of a reversible process per absolute temperature. So here that is ds is equal to dq reversible by T. This is a formula. Here the S represents the entropy, Q represents the heat transferred, T represents the absolute temperature. Next one is the applications of second law of thermodynamics. In various fields, the second law of thermodynamics is applicable to explain or to optimize the process. For example, engineering, physics, chemistry, biology, and environmental sciences, etc. Here are some examples used in that. The second law of thermodynamics is used to increase the efficiency or optimize the processes. For example, heat engines, refrigeration and air conditioning, chemical reactions, power generation, environmental science, biological sciences, and entropy generation. Next one is next content in that reversible and irreversible process. In thermodynamics, all of the process, any of the process comes to any of the category, that is reversible process or irreversible process. First, what is the reversible process? Reversible process means we can see reversible process means when the one process is changing from A to B in that duration. Anywhere in that duration, if I do any changes in the system properties like temperature and pressure, then if the system is reversing, the system is moving to initial condition, then we can say that the process is reversible process. In other words, the system changes its states in such a way that it can be reversed by an infinitesimal change in the condition. For example, temperature and pressure of the system or its surrounding. Here we can see the image. So that is a cylinder. In that cylinder, piston is there. When the load is applied on the piston, initially the the piston is loaded with the weights. When the loads are removing one by one, the piston is moving towards upward. Again, when we started applying the loads on the piston, is coming to initial condition. So from this is initial condition, and when you apply this, when we removing the loads, it went to one process, and when we apply again the loads, and it coming back to the initial condition. If that is the case, then it is called reversible process. When in this process, for example, in this process, in initial condition, you started removing the loads, but after some time you started again applying the loads, and that will, if that is the coming to the initial condition, then you can say that this is a reversible process. So at every stage of reversible process, the system is equilibrium with its surroundings. Generally, these reversible processes are the idealized process, and these are the benchmark for the real process. In a real world, we don't have a completely reversible process, but the frictionless piston cylinder system is, we can consider the completely reversible process. Next one is the irreversible process. In irreversible process, when the process is moving from one state to another state, during that situation, if you apply any external conditions like a temperature and pressure, it won't reach to the initial condition some amount that is irrevocable. If that is the situation, these processes are called irreversible process. Generally, these irreversible processes are spontaneous process. During the irreversible process, the system and surroundings experience an irrevocable change in their state. Irreversible processes are typically in real-world applications, real-world systems. Friction, heat losses, and chemical reactions are the factors for irreversibility. Here are some practical examples of irreversible process. For example, dropping a ball on a clay. Second one, hammering a nail. Applying the brake to the car. Next one is breaking a glass or egg, heating a food, burning a coil. For example, applying the brake to the car. When you apply the brake, the car is stopped. But after releasing the brake, it cannot move further without increasing the accelerator. Means, so like in a dropping a ball, when you drop it on the clay, it will stay, it can come back to the initial condition. So these are the example. In a food also, when it is a cooked, food is cooked, so after when you apply the heat, the food is cooked. When you remove the heat, it cannot come back to the initial condition. So these are the irreversible process examples. Next one is the Carnot cycle. The Nicholas Sadi Carnot in 1824 introduced a concept of cyclic operations. This cyclic operation is the ideal operation. Any process or equipment use this cyclic operation, it can be achieved the maximum efficiency. So that's the reason this cycle is known as the ideal cycle. So this is also known as a Carnot cycle. It consists of two irreversible isothermal process and two irreversible adiabatic process. They happen alternatively. We can see here the Carnot cycle diagram. So x-axis is the volume and y-axis is the pressure. So first one is a isothermal expansion. Next one is the adiabatic expansion. Next one is the isothermal compression, adiabatic compression. In these two isothermal reversible processes are there, two adiabatic reversible processes are there. Okay, so what this Carnot cycle says, when the heat engine run on based on this cycle, then from that heat engine you will get the maximum efficiency. So, for example, here we see, so the cylinder, this is a cylinder and this is a piston. Initially, isothermal expansion. From this is initial condition, isothermal expansion. It is moving up, isothermal expansion. Next one is the after expansion, adiabatic expansion, further moving up. After that, isothermal compression means at constant temperature compression and at no heat loss compression. So this is a steam engine. This is a two-stroke engine. Initially, the fuel is entered into the cylinder. When it is when the combustion takes place, the fluid has to expand isothermally. Then after that adiabatic expansion. The adiabatic expansion, because isothermal expansion means no at constant temperature expansion. After that, no heat loss expansion, so that whatever the heat is emitted, so that is converted into the work. After that, next isothermal compression. When is the cylinder is compressing, that generally temperature will raises. That's the reason the exhaust is open, so that isothermal compression. After that, again adiabatic compression. So if the engine works on this cycle, then you can get the maximum efficiency. That's the reason it is called Carnot cycle. So these are the four cycle. First, isothermal expansion. In this state, the working substance, generally often as gas, absorb heat from a high temperature reservoir. High temperature reservoir is the fuel. The gas, it will absorb the heat from the high fuel and at constant temperature, that is TH. During this process, the gas expanded and does the work on the surroundings. Next one is after the isothermal expansion, adiabatic expansion, there is no heat loss. In this stage, the working substance, that is gas, continues to expand without exchanging the heat with the surrounding. As a result, the temperature of the gas decreases. So that means that is converted into the work. Next, isothermal compression. Heat rejection at a constant temperature. In this stage, working substance is brought into contact with a low temperature reservoir. Heat sinks means the heat will be released at the constant temperature, that is TC, and it releases the heat to the surrounding. During this process, the gas is compressed and the work is done on it. Next one, adiabatic compression, no heat transfer. In this stage, the working substance is compressed further without any heat exchange with the surroundings. The temperature of the gas increases during this process. Okay, this is the Carnot cycle. The Carnot cycle efficiency can be defined as ratio of work output to the heat input from the high temperature reservoir. The ratio of work output to the heat input from the high temperature reservoir. So this efficiency can be explained in other terms also, like because the maximum efficiency of any heat engine operating between two reservoirs, high temperature reservoir at a low temperature reservoir. That's the reason the work is equal to the temperature difference between them. That is TH minus TC, and the next one is QH. You can write in terms of heat at TH also. So now efficiency is equal to TH minus TC by means high temperature reservoir at high temperature minus to reservoir at low temperature, difference by reservoir at a high temperature. Next one is the TS diagram. So the TS diagram is the visual representation of changing of entropy with the changing of temperature. For example, in any thermodynamic system, when the temperature is changing, then how the entropy is changing in that system. So that we can see using this TS diagram visually. We can see how the temperature is, when the temperature is changing of the system, how the entropy is changing. So this is explained by the TS diagram. It helps to visualize the heat transfer during the process. For reversible process, the area under the TS curve of a process is heat transfer to the system during that process. Means whatever the curve is there in the TS diagram, the area under the curve is equal to the work done by the system, or heat transfer to the system during that process. Working fluids are often categorized on the basis of the shape of their TS diagram. So in the TS diagram, the working fluid, what is the shape of the fluid? What is the shape of that? Based on that, we can categorize. These are because the area under the curve determines the work done by the system or fluid. So that if that fluid is doing high amount of work, so that we can categorize these fluids can do the high amount of work with the heat, and these fluids low end of work with it. We can categorize like that. So this is the TS diagram looks like. The at x-axis x-axis denoted with entropy, y-axis denoted by the temperature. So in this TS diagram, this curve represents the partition of the fluids, partition of the phase. Means the left hand side of this curve is the liquid state. Right hand side of this curve represents the vapor state. Now, under this curve it is a saturated state, that is a liquid plus vapor state. So generally at constant temperature, means this TS diagram can be applied for the various process. For example, isothermal process means the process is happening at a constant temperature. If that is the case, in this diagram, these lines looks straight, horizontal lines. Isentropy process. Isentropy means at constant entropy. At constant entropy, in this diagram, these constant entropy processes are looking like a straight lines. So when you see this diagram, this curve, initially the fluid at a liquid state, and when the temperature is changing, the entropy is changing, then after that is entered into the saturated state, then it is next one in a gas state, how the when the temperature is changing, how the entropy is changing. This is we can see that. So these curves at constant pressure. So these are the curves. These lines shows the constant pressure. These dotted line shows the constant volume. At particular pressure. How at particular pressure, when the temperature is changing of that particular fluid, how the entropy is changing. And next, if we increase the pressure, when the temperature is changing, how the entropy changing of that particular system. So like this point shows the critical point. Critical point above this point is called a super saturated state. So these are very useful diagrams in the thermodynamics. So we can see this is a TS diagram of water. We can see this is a solid region and this is a saturated region, and this is a vapor region, and so this is a supercritical region. So this line shows with a different pressures how the entropy is changing with respect to the temperature, and at constant pressure, at constant volume also, how the entropy is changing. With respect to pressure, temperature. The next topic is the enthalpy of mixing and disorder of mixing. Actually, this enthalpy of mixing and disorder of mixing, that's very important concept, because in thermodynamics generally we deal with the mixtures of the compound. First one is the enthalpy of mixing. So generally enthalpy is the it is denoted as delta H, that is equal to U plus P delta V, or H is equal to U plus P V. This is enthalpy formula. What is the meaning of that? The enthalpy of any system is equal to the internal energy of the system plus pressure of the system and volume of the system. So that is the enthalpy of the system. Okay. So the enthalpy is a measure of total heat energy of the system. So when two compounds mix, so sometimes energy may release or energy may absorb. Means the enthalpy may means what is the meaning of that? When the two compounds are mixed, the enthalpy there is a change in enthalpy. Okay, so for example, the enthalpy of mixing can be either exothermic, means when we mix the two compounds, the energy may release or energy may absorb. That depends on the compounds. In ideal situations, in ideal solutions, when you add two compounds, there is no change in the enthalpy of mixing. But generally, real situation, when we add two compounds, there is a change in the enthalpy. So this is, for example, if the molecules of the different substance attract each other, means if the favorable interactions are there between these two compounds, then the energy is released. Otherwise, when the A and B two compounds are mixed, there are no favorable interaction, then the energy is absorbed. That is called previous one is the exothermic reaction. Next one is the endothermic processes. Next one is the disorder of mixing. Means, in other words, when we add two compounds, what is happening to the entropy? We know the entropy. Entropy is also, and disorder is also known as entropy. It is a measure of randomness or the number of possible microscopic configuration of the system. Entropy is in other words, entropy is the randomness of the process. So when the two compounds are mixed, what is happening to the entropy? So generally, when the two compounds are mixed, the probability increases. That's the reason entropy increases. The increase in disorder upon mixing is often driven by the tendency of the system to maximize their entropy. Next one is refrigeration and liquefaction. So first we will see what is the refrigeration. Refrigeration means reducing the temperature when it is compared to reducing the temperature and maintaining that temperature when it is compared to the room temperature. Okay, so refrigeration finds wide applications in a pharmaceutical process industries. For example, ice making, next dehydration from the gases, means purification of the gases, and purification of lubricating oils. And if you want to conduct the low temperature reactions, the refrigeration is useful. And in refrigeration also, so many household applications are there, like in air conditioning, transportation, and food preservation. So generally, the heat can transfer from high temperature to low temperature spontaneously. But refrigeration means developing and maintaining that low temperature. In refrigeration, what is happening? The low temperature heat has to transfer from low temperature to high temperature. So, but it won't occur spontaneously. So that we need to do some amount of work. So what is that work? Okay. So we can see here from this diagram, the low temperature reservoir is there with at Q2 heat, high temperature reservoir is there, that is a Q1 at heat. So in a refrigeration, the heat is transferred from the low temperature reservoir to high temperature reservoir. So, if you want to transfer the heat from the low temperature reservoir to high temperature reservoir, we need to do work. Okay, that is W. So, according to the first law of thermodynamics, input energies is equal to output energies. G's. Okay, so what are the input energy? That is Q2 plus W is equal, because these are in and this is also in, that is equal to Q1. Okay, so from here W is equal to Q1 minus Q2. So we need to do this amount of work to transfer this. We need to do this amount of work, means that the difference between the two temperatures. For example, at the reservoir, the temperature is, for example, 0 degree centigrade. And the high temperature reservoir temperature at around maybe 50 degree temperature. So 0 to 50, if you want to transfer, so we need to do like 50 means joules of work. So for example, from 0 degree temperature to we want to do only 10 degree temperature. The high temperature is at 10 degree centigrade. Then, so we need to do only 10 joules of work only. So means the temperature difference between them, that much we need to do that work. Next one is the coefficient of performance of refrigeration. The coefficient of performance of a refrigerator is defined as the quantity of heat absorbed at low temperature per unit of work. The coefficient of performance is the quantity of heat absorbed per unit of work. So COP is equal to Q2 by W. We know already W is equal to, so COP is equal to Q2 by, that is W is equal to Q1 minus Q2. Okay. So we can write this one in terms of temperature also, that is T2 by T1 minus T2. Okay. Now COP is equal to Q2 by W is equal to T2 by T1 minus T2. So we can write, so W is equal to, from there we can write W is equal to Q2 into T1 minus T2 by T2. So this is the amount of work you need to do in terms of temperatures, and so this is the what is the coefficient of performance, means that refrigerator, what is the performance of that refrigerator? It depends on the heat absorption at low temperature by amount of work. Next one is the Carnot cycle for the refrigeration. Actually, we are already seeing that Carnot cycle is the ideal cycle. When you use this cycle, you will get the maximum efficiency. Okay, so this refrigeration process also works at two reservoirs, high temperature reservoir and low temperature reservoir. That's the reason what is the Carnot cycle, so that you can get the maximum efficiency. The Carnot cycle is here is the first we need to do adiabatic compression. After that, isothermal heat rejection. After that, adiabatic expansion. After that, isothermal heat absorption. Okay, so when the refrigeration process is operating at this cycle or in this cycle, then only you will get the maximum efficiency. That is a Carnot cycle for refrigeration. Next, choice of refrigerant. How to choose the refrigerant? Because so first the refrigerant has to go through the adiabatic expansion. When it is gone to adiabatic expansion, what is happening? Because of the expansion, pressure is reducing. Because means the generally the capillary tube or throttle valve is used for the expansion process. When the refrigerant is gone through this throttling valve, the the pressure is reduced drastically. Because of that, pressure is reducing, temperature also reducing. After that, that will send to the heat rejection, means the heat transfer between the food or heat transfer between the preservation of that item and refrigerant. After that, because the heat is absorbed, absorbed by the refrigerant, that's the reason, and that is completely converted into the vapor. So that we need to do adiabatic. The refrigerant is compressed, the gas refrigerant is compressed. Then after that, because of the compression, the heat temperature is rises, so that heat rejection, the isothermal at constant temperature, we need to reduce the temperature in the isothermal heat rejection process. After that, it has to adiabatic expansion, means at constant, without at no heat transfer, we need to expand, so that in a throttling valve, so that the fluid is expanded, so that the pressure is reduced, so that the temperature is also reduced. After that, isothermal heat absorption. When you do the refrigeration process using the refrigerant in this manner, so that you will get the maximum efficiency. Now, choose a refrigerant. So actually, a lot of research has been done on this refrigerant, so that number of refrigerants are now available in the market. But the widely used refrigerant is the Freon 12, because it is a non-toxic, non-flammable and non-explosive. Apart from it, other refrigerants are also in use. There are methyl chloride, carbon dioxide, sulfur dioxide, propane and ammonia. So these are the other refrigerant. So for example, so in your refrigeration process, if you want to choose your own refrigerant, so you need to consider these properties before choosing that refrigerant. First, boiling temperature of the refrigerant. The boiling temperature of the refrigerant must be lower than the refrigeration temperature. For example, if you want to maintain the refrigeration temperature at 0 degrees centigrade, then the boiling point of your refrigerant must be lower than the 0 degrees centigrade. Next, freezing point. The refrigerant freezing point should be lower than the desired temperature. So the desired refrigeration temperature. In the same way, for example, desired temperature is 0 degrees centigrade. Okay, so freezing point, for example, coming to the boiling point, the refrigerant boiling point should be lesser than lower than the 0 degree centigrade, means maybe, for example, minus 10 degrees centigrade. Freezing point also, whatever the refrigeration temperature you want to maintain, compared to that, freezing point also lesser than that. Next, critical temperature and pressure. The critical temperature and pressure must be greater than the desired refrigeration temperature. For example, I am saying. Okay. Next one, condenser pressure and evaporator pressure. In a condenser, the fluid is condensing. What is the pressure in that condenser? And evaporator, expansion process. In the expansion process, the what is the pressure in that. So generally in a condenser and evaporator, the pressure must be maintained not very high, moderately you need to maintain. So that you need to choose your refrigerant which are having moderate condenser pressure and moderate evaporator pressure. Next one is the specific volume. The specific volume says volume for unit mass. That is the specific volume. Volume definition. Okay, the specific volume means per unit mass. For what is the volume it is occupied. For example, you take the same weight of sponge and same weight of stone. So the sponge occupies per unit weight huge amount of volume, but the stone same amount of weight it occupies less amount of space, volume. Okay, means the specific volume decides what is the size of the compressor. Okay, so if whatever the refrigerant you invented or you want to choose, if the specific volume of your refrigerant is very high, then you need to choose the reciprocating compressor. If your refrigerant specific volume is less, then you can go for the centrifugal compressors. Next one is the latent heat. Latent heat is the minimum heat is required to change its phase. For example, water is there, you are supplying the heat to the water. So initially the temperature rises. After 100 degrees centigrade, how much temperature you supply, the water maintain it 100 only. Means whatever the remaining amount of heat is converting into a latent heat, so that the phase is changed. So here the latent heat of your refrigerant must be high. Okay. Next one, specific heat of liquid. So specific means heat means from the Q is equal to M Cp delta T. From here Cp is the specific heat. So Cp is equal to Q by M delta T. So what is specific heat is? To raise the 1 degree centigrade in the fluid, how much amount of heat you require. For example, you take the honey and you take the water. If you want to raise the 1 degree centigrade in the honey, what amount of heat you require? In the same way, to raise the 1 degree centigrade in water, what amount of heat energy you require? And generally, the honey is a very viscous fluid. With the specific heat of that honey is very high. That's the reason you need high amount of heat is required to raise the 1 degree centigrade in the honey. But in a water, lesser than the honey. So the specific heat of your refrigerant must be low. Means in other words, low viscous refrigerants are desirable. Molecular weight. So if the molecular weight is very high, so then and also means that the molecular weight of the refrigerant decides the compressor size. Okay, if the molecular weight of your refrigerant is very high, then choose a reciprocating pump. Low molecular weight of your refrigerant is preferable for the high molecular weight of refrigerant preferable to centrifugal pumps. Low molecular weight of refrigerant are preferable of reciprocating pumps. Next one, the safety aspects. Generally, the safety aspects are classified into 3 categories. One is the first non-flammable and non-toxic. This is the first category. Next one is the non-flammable or non-toxic. Third one is flammable and toxic. So the whatever the refrigerant you are going to choose, which category it is coming? Is a non-flammable and non-toxic? These are more preferable. Non-flammable or means either non-flammable or maybe it is non-flammable only. It is not a it is a toxic. Like that. Are flammable and toxic. So based on the circumstances, for example, in your system, there are no operating conditions that will help you to explode. In that case, you can choose. For example, you can choose flammable, but is a non-toxic. So, like based on circumstances, you can choose. Next one, other desirable properties. Because the refrigerant will stay in the refrigeration process for a long duration. That's the reason the refrigerant must be chemically stable, non-corrosive, low viscosity, and high thermal conductivity. So these are the preferable. Next one is the liquefaction. So converting a natural gas into liquid is a liquefaction. Nowadays, it has a wide range of applications, especially because of the transportation, easy handling, and easy storage. So liquefaction is used in the industry in a various applications. For example, separating or purification of gases. Okay. Apart from that, this liquefaction is other practical applications are liquid hydrogen and nitrogen are widely used in the missiles and rockets, and liquid helium is used in the space research. Liquid hydrogen is used in the nuclear weapons. So here the liquefaction means converting the natural gases into liquids. Actually, there are two categories. There are three types of types we can convert the natural gas into liquids. That is evaporation of liquid, Joule-Thomson expansion of gas in engine, and delivering the external work. Now here we see only two methods. First one is the liquefaction, vaporization of liquid method. The vaporization of liquid method is nothing else. The gas will send through the series of refrigerant. So this refrigerant boiling temperatures are when is compared to other is lesser than others. For example, initially, when you see here, the vapor is initially the vapor or gas state compound is sending to the first through the first refrigerant. The boiling point of this refrigerant is for example T1. So after that, when you say the heat, the refrigerant, the heat exchange, the heat is transferred between the gas and refrigerant, so that the refrigerant temperature is raised. The raised temperature is sent to the next refrigerant. It has a higher boiling point when it is compared to the first one. In the same manner, third one higher boiling point to the second one. Fourth one higher boiling point to the third one. Like that. So the last one, the whatever the heat is absorbed by this refrigerant, that will be emitted to the atmosphere to bring it to the in a liquid condition. So in this manner, when you send the gas through series of refrigerants, so the gas is converted into the liquid state. This is the vaporization of the liquid. So this method has been used for liquefaction of air and natural gas. The lowest temperature that can be attained by this method is 63 Kelvin. Next one is the liquefaction. So, next one is the Joule-Thomson expansion. Joule-Thomson expansion is the one principle. That principle says if you want to convert the gas into liquid state, initially you need to abruptly increase the pressure. Then only you can convert the gas into liquid state. That this is a graph says that. So the pressure has to be increased abruptly. So that is A to B. So the temperature raised. So after that, B to C, you need to decrease the temperature. C to D, again further decrease the temperature, and after that, and D to E is the gas is converted into the saturated phase. From there, we can separate the E to F and E to G. So this is means the Joule-Thomson method is a principle that says if you want to convert the gas into liquid, initially abruptly you need to increase the temperature, increase the pressure. Then only it is possible. So based on this principle, the Linde process is developed for the gas liquefaction. In that, the gas is sent from the compressor, that is A to B. So you can see A to B, the compressor is used, so that the temperature is raised. So the B to C temperature is reduced using the cooling. The temperature is reduced using the cooling. And C to D again, the heat is exchanged in the heat exchanger, so that it reaches to C to D. Again, from the D to E, when it is sent to the D from through the throttling valve or capillary tube, so because of the pressure is reduced, the temperature is reduced, so that the fluid is converted into the liquid. Okay, so here that is a E. So this we says that there is a TS diagram. This is a saturated phase. Okay, so the liquid is when at a constant temperature, isothermal process decrease the entropy, then that is the E to F. So you can separate the liquid. So whatever the gas is, they remain that G2 you can send to again to the heat exchanger, from the heat exchanger to again A. So same initial condition. So these are called Linde process for gas liquefaction. Generally, using this process, the oxygen is converted into liquid state. Okay. So with this, we completed the first unit content. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.